Imagine finding a single spelling mistake on page 47 of a massive 1,000-page novel you just printed.
To fix that localized error under the current paradigm, you would print 32 entirely new copies of the entire book.
Hoping one of those new copies randomly corrects the typo without, introducing new formatting issues elsewhere.
You then sit down to read all 32 massive volumes, pick the best one, and throw the other 31 copies in the trash.
It sounds completely irrational, but right now that is the literal methodology your computer uses when you ask artificial intelligence to edit a photo.
Welcome to the deep dive. We are exploring a highly technical paper titled From Scale to Speed: Adaptive Test Time Scaling for Image Editing.
Our mission today is to examine why simply throwing more computing power at AI image editing is a massive bottleneck. We are unpacking a framework called ADE-CoT, which stands for Adaptive Edit-CoT.
As users of these generation tools, you might assume that forcing the machine to generate more options guarantees a better result.
We will reveal why that brute force approach actually backfires. Teaching an AI a simple concept, knowing when to stop, actually creates a massive 2-time speedup in processing.
To understand the necessity of ADE-CoT, we have to look at the mechanics of the system it replaces. The standard approach is known as image chain of thought, utilizing a sampling strategy called best of n.
This is a test time scaling paradigm. It improves image generation by simply extending the inference time,
Providing a training-free solution to boost quality by giving the computer a larger budget of attempts. This strategy works exceptionally well for text-to-image generation because creating an image from scratch is an open-ended task.
If you prompt a system to generate a cat running on the ground, the resolution space is vast.
Producing a large scale of samples through noise perturbations yields diverse, highly plausible outputs. You benefit from seeing 30 different creative interpretations of that open-ended prompt.
Image editing is fundamentally different because it is goal-directed. The solution space is strictly constrained by the source image you provide, alongside a specific instruction.
Uploading a picture of a specific character and typing the prompt, add a cherry-eating action, means the AI is not supposed to take creative liberties.
It shouldn't invent a new background or alter the lighting. The source text identifies 3 major flaws when applying open-ended methods to a highly constrained editing task.
The first flaw the authors note is inefficient resource allocation. Existing methods use a fixed sampling budget,
meaning they generate an arbitrary number of samples, usually n equals 32, for every single edit.
That fixed budget drains computational power on simple edits that show minimal improvement from large-scale sampling. The second major flaw is unreliable early-stage verification.
Previous systems try to save computing costs by evaluating intermediate denoising states.
General multimodal large language models, or MLLMs, are used to score these early, noisy previews.
Distinguishing a small change, like adding a cherry to someone's hand, is incredibly difficult when looking at a blurry, static-filled preview.
The data reveals a massive error rate due to that difficulty. 40% of samples that score very low at these early stages actually go on to achieve high final scores when fully rendered.
Those are high-potential candidates getting incorrectly pruned before they even finish processing.
The general evaluator misinterprets the localized edit as a failure, severely degrading the final performance of the system.
Which leads into the third major flaw, the paper highlights: redundant results. Large-scale sampling and editing frequently generates multiple correct outputs with identical top scores.
The paper notes that for edit cases with best scores in the 7 to 9 range, the system often generates over 15 candidates sharing that identical score.
Evaluating all of them is comparable to asking a chef to make 32 identical sandwiches just to find the one with the perfect spread of mayonnaise.
Rather than just tasting and adjusting a single sandwich as they go, it is a staggering waste of time to render identical correct outputs when you only need one intent-aligned result.
Addressing that core inefficiency leads directly to ADE-CoT's first strategy, which is difficulty-aware resource allocation.
The framework completely eliminates that fixed sampling budget of 32. The system acts dynamically based on a mathematical estimation of the edit's difficulty.
Given your source image and instruction, ADE-CoT generates a single candidate to obtain an initial score.
This initial score acts as a direct proxy to determine how hard the edit is. The system applies a specific mathematical formulation utilizing a sensitivity threshold denoted as the Greek letter gamma.
With gamma set to 0.15, simple edits that achieve high initial scores receive a minimal sampling budget.
Complex edits returning low initial scores trigger an expanded search budget.
Let's pause and look at the risk there. If the AI happens to generate a weirdly good first image by pure statistical chance, does judging the difficulty off a single first attempt risk misclassifying a complex task?
The architecture accounts for this probability issue by using that initial score strictly as a calibrated proxy to assign the budget, rather than a definitive final judgment.
You could end up under-budgeting a hard job if it was a low probability success on step one.
The mathematical curve dictated by the gamma parameter is the safeguard here. It ensures the budget smoothly converges toward the minimum threshold only for incredibly obvious successes.
Rapidly scaling up toward the maximum budget for anything that registers as remotely ambiguous.
Testing showed that increasing gamma from 0 steadily reduces the number of function evaluations, the computational steps required, up until gamma exceeds 0.15.
Proving the initial check is a reliable mechanism to prevent wasting computing power on edits that demonstrably will not benefit from further sampling.
We have established a smart, dynamic budget, but that creates a new logistical problem.
Generating fewer images overall means we need a way to evaluate them early in the process without making that 40% misjudgment error we discussed earlier.
Solving that evaluation gap requires abandoning those general scores for early stages. ADE-CoT uses its second strategy, edit-specific verification, in early pruning.
The first component of this strategy is a mechanism called a one-step preview.
Standard pruning requires running additional denoising steps to get a clear enough picture for an evaluator, costing extra computational power.
Recent editing models utilize a concept called flow matching, allowing ADE-CoT to estimate the approximate clean latent image from early noisy states in a single step.
Think of flow matching like observing the initial trajectory of a moving object. The system can mathematically predict the final destination of the pixel data without simulating every step of the journey.
It is like seeing the architectural blueprint instead of building the entire house just to see if the kitchen layout works.
With that structural preview generated, the framework implements a strict check for edited region correctness. A primary failure in AI image editing is the mislocalization of edits.
The AI changing things that should absolutely remain untouched.
ADE-CoT prompts the language model to identify the specific object to modify. That target data is fed into Grounded SAM2, an advanced segmentation model.
Grounded SAM2 creates a strict binary mask of the expected edit region.
The framework computes a per-pixel change map by averaging the absolute color differences between your original source image and the generated preview.
Aggregating these visual changes exclusively within that binary mask to generate a region score. It is like checking the quality of a house painter's work.
By using a specialized overlay.
You do not stand down the street and look at the whole house through a fog. You place a physical stencil over the front door to guarantee that not a single drop of paint hit the surrounding brick wall.
By isolating the evaluation to that specific region, the system avoids penalizing a great edit just because the surrounding unedited areas still look noisy in the preview phase.
Following that region check, the system evaluates instruction caption consistency.
Checking the semantic similarity between an edited image and a ground truth caption is a standard metric, but in a live test time scenario, ground truth captions do not exist.
There is no answer key when a user is just uploading an image.
The framework instructs a language model to generate a targeted caption conditioned on your source image and your specific edit instruction,
acting as its own narrator. The system computes an image caption consistency score using a tool called CLIP, comparing the generated image to that highly specific narrative text.
The region score and the caption score are combined with the general score to form a unified evaluation metric.
The data shows this unified metric reduces the misjudgment of high-potential candidates by an impressive 63% compared to using general scores alone.
Evaluating regions and captions efficiently still leaves the issue of the AI generating 15 identical correct images behind the scenes.
The framework needs to know they are redundant without fully rendering them.
ADE-CoT deploys a visual similarity filter using a model called DOV2 to extract visual embeddings from each preview.
Translating the core visual characteristics of the image into a mathematical summary, or a vector, rather than comparing them pixel by pixel.
It computes the pairwise similarity between these mathematical summaries. If the similarity score between two previews exceeds a specific threshold, they are functionally identical.
The system instantly discards the candidate with the lower unified evaluation score.
guaranteeing that only visually distinct and high-potential candidates remain in the pool for the subsequent generation stages.
Avoiding the computational costs of processing identical images, we are left with a curated pool of highly distinct candidates.
As these remaining images continue through the late denoising stages to become fully polished outputs, we need to stop the system from obsessively rendering every single one of them.
Bringing us to ADE-CoT's third and final strategy, depth-first opportunistic stopping.
Previous pruning strategies rely on breadth-first search, generating all candidates in parallel and pushing every image through every computation step before making a final selection.
ADE-CoT changes the paradigm by processing the remaining candidates sequentially, ordering them by their early-stage scores.
The process incorporates a late-stage filter at a further time step to retain only the candidates with scores comparable to the current highest score,
Dynamically pruning suboptimal samples as they render. A critical element of making this stopping strategy work is the instance-specific verifier.
General MLLM scores often assign the exact same top scores to multiple candidates, even when some contain glaring editing errors.
The text provides a fascinating visual example. The baseline model gave a highly rated general score to an image of a person with their head turned sideways,
Despite the user's prompt specifically asking for the subject to look forward.
the general verifier missed the subtle semantic failure entirely because the overall image was aesthetically pleasing.
To catch those nuanced semantic failures, the instance-specific verifier utilizes a two-stage inquiry mechanism. First, generating a set of targeted yes or no questions about the specific edit.
Covering both instruction adherence and overall aesthetics. Returning to the sideways head example, the verifier automatically generated a highly specific question.
Are the shoulders aligned to indicate a forward-facing posture?
The system uses a vision language model to answer its own generated questions based on the rendering image, producing a final score by counting the affirmative responses.
Candidates with semantic errors are heavily penalized. Because the system processes these images sequentially in a depth-first manner, it can stop the search.
The moment it accumulates a sufficient number of intent-aligned results, meaning images that receive affirmative answers to those targeted questions.
The default setting the authors use stops the search the moment it finds 4 intent-aligned results.
This concept is highly relatable to typical human workflows. You see people overwork a project, endlessly tweaking a design when it was perfectly aligned with the goal 3 versions ago.
ADE-CoT codifies the wisdom of recognizing when a goal has been successfully achieved, implementing a strict mechanical rule to simply stop computing.
Preventing the system from burning energy on unnecessary perfectionism. Integrating all 3 of these core components yields incredibly impressive empirical results.
ADE-CoT was evaluated on 3 state-of-the-art open-sourced image editing models, Step 1 Xedit, BAGEL, and FLUX.1 Kontext.
The testing spanned 3 comprehensive benchmarks. GetItBench covers real-world user edits.
Any edit test evaluates local, global, and implicit editing tasks. Reason Edit involves complex understanding and reasoning scenarios.
Across all these diverse testing environments, ADE-CoT achieves more than a 2 times speedup over the standard best event approach.
While maintaining or even improving the actual quality of the generated images, the researchers categorize these performance improvements through 2 specific efficiency metrics.
The first is reasoning efficiency, denoted by the Greek letter eta, which measures the overall trade-off between performance and computational cost.
ADE-CoT improves reasoning efficiency by over 2 times compared to best event. The second metric is outcome efficiency, denoted by the Greek letter alother.
This quantifies the reduction in redundant computation. Think of outcome efficiency like searching for your keys in your house.
If you start in the living room and find your keys on the coffee table, you do not systematically search the bedroom, the kitchen, and the garage.
By giving the AI permission to stop the search early once the keys are found, ADE-CoT increases outcome efficiency drastically.
Showing an average increase of 4.9 times on GetItBench, 2.7 times on AnyEdit, and 2.9 times on Reason Edit.
The scaling curves documented within the data confirm this massive efficiency advantage comprehensively.
When comparing methods that achieve non-degraded quality relative to the baseline, ADE-CoT requires significantly fewer number of function evaluations.
Alternate pruning strategies tested in the study, such as PRM, PARM, and TTSEF, showed limited performance gains or lower overall efficiency.
PRM and PARM struggled specifically because they relied on those general scores, incorrectly discarding high-potential previews early on.
PTSEF suffered because selecting only a single best sample from early previews becomes mathematically unreliable when you scale up the complexity.
ADE-CoT hybrid search approach proves to be the optimal structure.
Utilizing a breadth-first approach in the early stage to preserve high-potential candidates using those region masks and captions.
Then switching to a depth-first approach in the late stage to sequentially finalize the best options and avoid unnecessary computation.
Beyond the raw efficiency metrics, the authors of the study documented a fascinating analytical insight regarding cases that simply never succeeded.
They noted that for certain highly complex samples, even after applying extensive Image-CoT sampling and allocating maximum computational resources, the evaluation scores never improved.
The AI simply could not accomplish the edit. The paper points out that this phenomenon serves as a diagnostic method.
Identifying the inherent capability boundaries of the foundational models themselves.
I want you to ponder this concept for a moment as we wrap up. We spend so much time trying to force these systems to succeed.
Analyzing the failures provides invaluable diagnostic data.
What if the true value of observing an artificial intelligence's failures isn't just about trying to fix those specific errors?
Using those unfixable moments as a cartographer's tool.
Mapping out the exact invisible borders of an artificial mind's imagination. By charting the specific coordinates where the model systematically fails, developers gain the precise data needed to understand the absolute limits of the system's current architecture.
Circling us right back to our massive 1,000-page book with the single spelling mistake.
We are no longer blindly printing 32 entire volumes just to throw 31 away in frustration.
Through adaptive test time scaling, we are learning to locate the specific page, apply the required edit using a targeted stencil, and stop the presses the moment the job is verified.
And perhaps most importantly, understand the absolute limits of the text itself.